Hello, everyone. I'm Joyce Zhou from Jacobs. I'm pleased here to introduce our work about the traffic simulation on active transportation management strategy in Pennsylvania. I'd also like to recognize Zhou working on this project together. Okay, here is the presentation agenda. First is an introduction on active traffic management and the project. And then I will talk about the methodology to develop the basic models and simulate the impacts of the ATM strategy on the traffic operation. At the end, I will summarize the findings from the analysis. In Pennsylvania, a quite portion of I-95 corridor runs through the developed urban area where the right-of-way is limited. This makes constructing new lanes or roadways is no longer a sustainable strategy considering the relatively high economic cost and the environmental concerns. Meanwhile, previous studies show in reality traffic conditions in the study area are rarely typical due to special events, weather, crashes, and other incidents, or some combination. In this case, new road construction is not a cost-efficient way to solve the congestion. On the other hand, the ATM, active transportation management, can dynamically manage both recurrent and non-recurrent congestion based on prevailing traffic conditions. ATM helps preserve and improve the performance of the transportation network by getting more use out of the current infrastructure. Implementing ATM strategy are generally the most cost-effective for those roadway segments where there is either persistent recurrent congestion or have the variable demand. Here are some widely deployed ATM strategies. Ramp metering deploys traffic signals at on-ramps to dynamically control the rate of vehicles entering a freeway vicinity, which could be able to smooth the mainline flows. Hard shoulder running uses the shoulder lanes as a travel lane based on congestion levels during peak period or in response to incidents. This strategy can temporarily provide additional capacity. Dynamic speed limits and lane assignment are usually implemented in conjunction with hard shoulder running, providing advanced warning of the lane open or closure, and informing the drivers the upcoming speed fluctuated segment. Queue warning is a real-time display of warning message to alert drivers that queues or significant slowdowns are ahead. It also may be included as part of dynamic speed limit strategy. Our project is aiming to evaluate the specific ATM influence on traffic operation along the I-95 in Pennsylvania. Due to the long corridor, the whole study area is divided into 4 sectors, and the first part of the analysis focuses on Sector C, as the figure shows. It's the southmost part of the I-95 corridor in Pennsylvania. It's a 15-mile long segment consisting of 30 interchanges and 28 adjacent intersections. Other than the I-95 corridor, this sector also contains a major branch, I-476, which is ending at the systemic interchange, and a major local arterial, PA-291, as the purple color shows. It is an important local alternative route within this area. According to the long-term transportation planning, the proposed ATM strategy should be eventually implemented after 2045. So in this study, the existing year for analysis is 2019, when the field data was collected, and the design year is 2045. This flowchart shows how the existing vessel model is developed and calibrated. The peak hour volume are determined based on the field data, including the mainline counts, ramp counts, and the intersection turning movement. After the balance peak hour volume set developed, the vessel network was used to generate the orange and destination pattern and the corresponding routes within the study area. As a starting point, the OD tables from the DVRPC travel demand model were adjusted using the VSUM tool flow fuzzy to match the traffic assignment to the field traffic and get the new estimated OD tables. This information was fed into the vessel model for calibration. Additional demand adjustments may be required as a result of the calibration process. The development for 2045 future models is similar, except the two major differences. The future peak hour volume are calculated based on existing volumes and the regional annual growth rate, which is derived from the existing TDM model and future TDM. Secondly, instead of using TDM OD table, the existing OD matrix is used as the seed table to estimate the future OD matrices in VSUM. The existing traffic data was connected from the field counts, e-rigs, and other resources in 2019. The data shows within the study area, the morning peak period is from 6:30 to 9:30, and the peak hour happened between 7:30 and 8:30. The model will simulate the whole 3-hour peak period, plus 30 minutes seeding time. In the morning, there are 3 major bottlenecks as shown in this figure. The first one is the merge area of US 1 on-ramp to I-476 northbound, which causes the significant congestion. The queue extends almost the whole northbound corridor until the system interchange. And on the southbound, it's similarly. The US 1 on-ramp merge area makes the traffic slow down here. And in addition, as these two interchanges are relatively close to each other, another merge area at Baldwin Pike prevents the speed to recover, so makes the whole segment as a slowed down area. And the third bottleneck is between I-476 and the US 322 on I-95 southbound here. One of primary reasons is the high density of the diverge and merge area. There are total 5 on-ramps and off-ramps within 3 miles on this road segment here. So as mentioned before, because of the right-of-way limit, it's not feasible to construct new lanes to mitigate the congestion. PennDOT had put a lot of efforts by deploying ramp metering at the on-ramps along I-476 through the 3 interchanges, US 1, Baltimore Pike, and McDade Boulevard. All the ramp meters is dual lane that allows 2 cars going through per green time. They can be coded in basin by using the traffic-dependent VAP programming. Here is a simulation video. The ramp metering does have controls on the flow rate entering the main line, like the video shows. However, due to the high demand along the whole corridor, we can still see the bottlenecks at the merge area, and the traffic slow down after that. The existing model simulation result also show the congestion conditions. Here is the I-470 northbound. The bottleneck at the US 1 and get a long queue behind that. And this is southbound. The whole segment between Baltimore Pike and the US 1 are bad. That's the congestion area. So regarding the future year, it's expected the traffic operation would be worse because of the regional demand growth. These speed diagrams illustrate the comparison between future year and the existing year. If there is no any improvement measures, the speed map will become like this for these three major bottlenecks. While the speed maps on the I-95 southbound look comparable between existing and the future, the queues on I-476 become significantly longer, especially on the southbound. In addition to the longer queue, a new bottleneck appears at the system interchange because the traffic from the I-476 southbound to I-95 southbound exceeds the on-ramp capacity. In this case, another ATM strategy, hard shoulder running, is considered. The left side shoulders along I-476 are proposed as the travel lanes during the peak period on both directions from McDade Boulevard to the north of the US 1. For I-95 southbound, the right side shoulder is open during the peak period between I-476 interchange and the US 322 interchange. Especially the ramp from I-476 to the I-95 southbound. This is one lane ramp existing condition, and in this proposal, it becomes the two-lane ramp with the shoulder lane open. So these are some examples that how the hard shoulder running is coded in the basin. Here, the green color represents the shoulder lanes. So this is on the left side on 476, right side on I-95. Okay. This is a future volume comparison when hard shoulder running is open or closed. The curves represent the demand on each segment, and the bars represent the unserved demand. It can be seen the opening of hard shoulder running would attract more demands due to the additional capacities provided by the shoulder lane. But the unserved demand percentages become lower. This means the capacity of the shoulder lane not only accommodates the induced demand, but also a portion of original demand. And from the speed maps, we can see that congestion on I-476 could be completely cleared with the hard shoulder running open on both directions. And the travel time diagrams are consistent with the speed maps. With a smoother traffic flow, when the shoulder is open, the travel time could be significantly reduced. On the northbound, the travel time from the about 40 minutes reduced to less than 10 minutes. And the southbound, there also have about 20 minutes reduction compared to the shoulder lanes closed. However, the operation on the I-95 southbound is different. With the hard shoulder rolling open, the travel time becomes longer, as shown by the gray curve here. And the orange, the blue one is the base condition with the hard shoulder rolling is off. So when the hard shoulder rolling is open, the speed map can show that the bottleneck still exists, but moves to downstream and generate a longer queue compared to the scenario when the shoulder is closed. In addition, the time span that the congestion continues become longer as well. It starts from the simulation beginning and lasts almost the whole peak period. So the new bottleneck is located at where the hard shoulder rolling ends, as this figure shows. Here is the hard shoulder ends here. And the major reason is the downstream road cannot accommodate the higher demand. This table compares the demands between two scenarios. When hard shoulder rolling is open, the hourly volume is about 400 higher than the base condition. But because there is one more lane, the demand per lane becomes lower. But when the hard shoulder rolling ends, the downstream road has the same number of lanes as the scenario that the shoulder lane is closed, while it leads to serve the higher total demand. Now the demand per lane is over 1,800 vehicles per hour, which creates the new bottleneck and makes the queue spill back. And so the analysis result shows simply implementing hard shoulder rolling is not necessarily mitigate the congestion. The opening of shoulder lanes would attract additional demand, which could be accommodated by the increased capacity on the hard shoulder rolling segment. However, if there is no capacity constraint after the hard shoulder rolling ends, the traffic operation could be significantly removed, like the performance showing along I-476. But once the downstream road capacity cannot accommodate the additional induced demand, the hard shoulder rolling may create a new congestion at the potential bottleneck location. Therefore, the more comprehensive strategy implementation should be considered. One of them is to cut off the opening time of the shoulder lane instead of the whole peak period. This could directly reduce the upstream demand before where the hard shoulder rolling ends. Another proposal is to combine the hard shoulder rolling with other ATM strategies, like dynamic speed limit or queue warning, giving the drivers an alert of congestion ahead. With the information, some drivers may choose alternative routes that also be able to reduce the upstream demand. These proposals and their combinations will be our concentration of the next step analysis. Any questions?
All right, thank you, Joyce, for the presentation. Do you mind just going back one slide to your summary?
Okay.
Conclusions, thank you. So what is your, I know you talked exhaustively on the findings, and I know you were looking at different corridors and directionality, but in this conclusion, it seems, at least on a casual observation of just first seeing this, that maybe the hard shoulder running is not a great idea. You know, what's your overall takeaway? Is it a, you know,
so basically, we can determinedly to say hard shoulder running can mitigate the congestion, necessarily mitigate the congestion. It depends on the specific traffic conditions. So the same hard shoulder running on the I-476 and I-95 southbound have the different result. One of the primary reason is on the I-476, there is no downstream capacity constraint. So the induced demand, the additional demand induced by the hard shoulder running can be served by downstream regular lanes. But on the I-95 southbound, the downstream capacity, the regular lane capacity cannot serve the additional demand attracted by the hard shoulder running. So that's created the new bottleneck. It solves the existing bottleneck, but creates a new bottleneck.
That makes a lot of sense, and that's a good point. Obviously you are intimately aware of everything in those corridors, and for somebody like myself that's seeing it for the first time, but that's a great summary. It makes a lot of sense, right? If you look at where your the hard shoulder running may terminate, what is the situation there? Does it have to merge back, or does it open up in terms of the capacity? Because definitely, like you're saying, based on the demand and those capacities, you may very well just be moving that bottleneck downstream. It was interesting to me that in your analysis that it did show that by doing that, at least in the one case, that it created such a large queuing and delay ramifications were worse than not doing it, if I understood your analysis correctly.
Yes, so that's why one of our next proposal would be the combined hard shoulder running with other ATM strategy. So as a control measure of the upstreaming demand. So yeah, that's our next step.
Okay, great. I got a couple questions that came in. So the first one is, how does the dynamic lane assignment work?
In this study, we haven't deployed the dynamic assignment lane. So we just simply open the add a lane as a shoulder lane, as a hard shoulder running, to give more capacity in the model. So, but the next, like I said, that's another propose, our next step propose. So we will try to model the management within this model, so we can flexibly open and close the hard shoulder lanes.
Okay.
In current model, the hard shoulder lane will open for the whole simulation time.
It is. So that was the next question. Was it open for the entire 3-hour period? And do you think extending or constricting it might improve the results? So is that, you're saying that some additional phases of the study that you're going to do?
Yeah, that's the next step. This make the hard shoulder running operation more flexible within the simulation time.
All right. Have you looked? The question is, have you looked at at the hard shoulder running for restricted use, like for just HOV vehicles or public transit?
Currently not. So now this is open for all the vehicle type.
Great. Let me see if any others. I feel like there's about to be one from my colleague, but I'm not sure. You get the 3 dots on these texting apps and you have all this hope, right? It's like personal text. Oh, good, she's replying right now. I didn't say something too bad, I hope. At any rate, we'll see. I'm going to have you hang on with me just for another minute, see if that question comes in, because I'm going to ask it. If not, then we'll take a few minutes. The 3 dots went away. Boy, now I feel sad. All right. At any rate, Joyce, thank you so much. Very good to see your modeling there. Very interesting to see. Oh, one just popped in from somebody else. Does the HSR lane go to the exit? That's a question.
You mean existing condition?
That's a good question. I'm not sure. The person typed it into the chat box here. Yes, existing condition.
No, there is no hard shoulder running for existing condition. Only the rev metering on the 476.
Okay. All right. And the other question did pop in. I knew if I, droned on long enough, we'd get it. So that's good. When looking at the potential downstream bottlenecks, are there any factors that could indicate issues? Maybe before even starting the analysis.
I'm sorry. Could you repeat the question?
Yeah,
again?
sure. When you're examining the corridor and looking at the potential downstream bottlenecks, is there anything that you might any factors that you would identify perhaps even before starting your analysis as indicative of that it could create issues with queuing and delays?
The one of factor could be the merge area downstreams. So in the existing condition, in the existing condition, this downstream is also a slowdown area because of the merge area and the diverge area. It's high density segment with the merge and the diverge. But the operation is not very bad. It's kind of slowed down. So after we open the hard shoulder running upstream a little bit, so more demand, more traffic, flash down to the downstream area. So that makes the current slowdown situation worse a lot. So that's why the new bottleneck was created.
Okay. All right. Thank you. I think that is all for the questions. So Joyce, thank you very much for presenting today. Very good to see your work there, and we appreciate it.
Okay. Thank you very much.